Hello everyone. Today we are going to be looking at summary of curve sketching. Now in the summary, we will be using all the things we have learned so far in our applications of differentials. We have talked about how to find the open intervals where the function is increasing or decreasing, where the functions are concave up or downwards, and also the limits at infinity. And also at the same time, we talked about finding the relative extrema of a function. So all of those things which we have learned, they will be utilized when we are going to analyze and sketch the graph of a function. So some guidelines. The first thing, we will find the domain of the function, the intercepts of the function, the asymptotes of the function. Now, when we talk of the asymptotes, we're going to look at the vertical asymptote, the horizontal asymptotes. We're looking at the intercepts. We're going to talk about the X intercept and the Y intercept. Then we will find the first derivative. It will help us to find our critical numbers. And from there, we will look at the open intervals where the function is increasing or decreasing. Then we will do our second derivative. And we'll find the x values where the second derivative does not exist or is 0, which will help us to get the intervals where the functions are concave up or concave down. And finally, use either the first derivative test or the second derivative test to determine the relative extrema of the function. Okay guys, let's begin with the examples. Now, we're going to start with a simple polynomial. It's a fourth degree polynomial. x4 minus 12x cubed plus 48x squared minus 64x. We would like to graph this function and analyze it. The best one, first we're going to do is write it in the factor form. It is x times x minus 4, the whole cube. And then we will start with the things we need according to the guideline. The first thing, it's a polynomial. The domain is the whole of R. We can write this as minus infinity to infinity. Now to find the x-intercepts, the factored form comes very healthy because remember, x-intercepts means y is 0. So that means 0 equals x times x minus 4 the whole cube, which gives us two x-intercepts, 0 and 0, 4 and 0. Now, what is the meaning of y-intercept? It means where x is 0. So that means y, which is x times x minus 4 the cube, is simply 0. Okay, so there is only one y-intercept. Now, talking about asymptotes. Remember, it's a polynomial. You're not going to have any asymptotes, vertical or horizontal. No ways. Okay, so we've taken care of these first 5 pointers in our guidelines. Now we're going to start with the first derivative to get our critical numbers. Now, the first derivative is 4x cubed minus 36x squared plus 96x minus 64. Now, to find the critical numbers, we put the first derivative to be 0. And what we see is we get a function by taking the 4 out, x cubed minus 9x squared plus 24x minus 16, which we can easily write it in the factored form, x minus 1 and x minus 4 to the power 4. So clearly from this, the two critical numbers are 1 and 4. Okay, now these are the ones which will give us the intervals. Now remember, from my previous notes that when we get our critical numbers, I always draw this little a number line, and I would draw little rectangles. And when I draw these rectangles, I would write critical numbers. So that helps me to get my little intervals. Okay. Now the first interval is from minus infinity to 1, the second 1 to 4, then 4 to infinity. Now, we need to know where the functions are, increasing, decreasing. What we do is we take the little test values. which is here, say negative infinity 1, I'm going to take a 0. Then 2 between 1 and 4, and a 5 between 4 and above. So f prime of 0, that means you plug in the value here, gives me negative 64. F prime of 2, that means you plug in the value here, f prime of 2, you plug it here, gives me 16. And when you plug in f prime of 5, again you get a 16. Okay, I hope so it's a 16, but what I definitely know, it is a positive number. Let's say this way. This is a positive number, and give me a second, I will check it too. Oh, yes, it is 16. I just plugged in the numbers here. In other words, I did, what I did was, I plugged the number in. This is my f prime of 5, because this is much more easy. So when I plugged f prime of 5, I had 4 times 5 minus 1, 5 minus 4 to the power 4, which is 4 times 4, and it is a 16. Okay, great. So what we notice, it is decreasing when it is from negative infinity to 1. So here it is decreasing. When f prime of 2, yes, it is increasing. Okay, and again it's increasing. So the intervals of decrease are negative infinity to 1, and increase are 1 to infinity. So that's how it is. Okay, let's look at, and also let's talk about things which we know, because we know the first derivative test just only needs information. So if you move according to the arrows, you see the function is going down and then up. So that means the point there, the function has a relative minima. So just from this one, we already know there's a relative minima at x equals 1. Okay, and now we also like to know the concavities. Okay, let's look at the concavity of the function. So first we take the second derivative, which is 12x squared minus 72x plus 96, and I need my intervals. We're going to put the second derivative to be 0, and we can write c, it can be written as 12 times x minus 4 times x minus 2 to be 0, easy to factor here. And so the test intervals are 2 and 4. So we need some test values, so pick up a 0, a 3, and a 5. And then you evaluate the second derivative at 0. We get 96. It's positive. Concave up. F's second derivative evaluated at 3 is negative 12. It is concave down. And F's second derivative at 5 is 36. Again, concave up. So concave. Okay, sorry, this is concave up, not concave down. Well, this is how the graph looks. So notice it has only one minima, and that it has 1. So it's a relative minimum at 1 and negative 27. And also there is a point of inflection, because concave up to concave down to concave up. So there's a point of inflection at let's see this one here. So it's from negative infinity to, remember this one here, 2. Okay, so let me write it here. So point of inflection is negative infinity to 2. So that means here is my point of inflection. 2 is the point of concave up to concave down. So this is concave up. So point of inflection is at 2 and f of 2. And again, the point of inflection is at, there's a change. Remember, concave down, it goes concave up at 4 and f of 4. Okay. So also, I forgot last time to talk about the intervals, concave up it is negative infinity till 2. You see, this is concave up. And then it is from 4 to infinity. This is where it goes. And concave down is from 2 to 4. Okay. We can easily figure out what are the point of inflections. So let's look at f of 2. What was our function? Let's go, and our function was, here's a function. This is our original function. So x4 minus 12. So basically we're going to look at this point. So 2 times 2 minus, okay. So let's write that down here. So f of 2 is x times x minus 4, the cube. So what is f of 2? It's 2 times minus 2 cube. That's minus 16. That's somewhere here. So the values for the inflection are 2 and minus 16. What about 4? 4 is 0. You can already see because that's where it is going. Because when you plug it here, it's a 0. 4 times 0 is a 0. So its point of inflection is 4 and 0. Okay, so here you have the graph and we have got all our information. So notice when you were drawing it, when we did the critical numbers in the open intervals, they were automatically giving us those, where the relative maxima and minima would have been. So what we can do also here is, remember, it is passing to the point 0. So we can also look at from this angle. So when you're drawing the graph, you have all the information. What I would recommend to you is look at the domain is the whole real numbers. So this is given, but I will still show you how to do. So the domain is, it's passing to the point 0, 0. Remember, the intercepts are 0 and 0, 4 and 0. So the thing you should be doing is, you should basically eyeball 0 and 0 and 4 and 0. Okay. Now, it has, now remember the, okay, so let me draw this little, the increasing. So 1 and 4, we had the function was decreasing, and then the function was increasing and increasing. And the point of inflection was at 2 and at 4. Okay, so that means eyeball 2 here, and somewhere here, negative 16. And the minimum is at 1 and negative 27, so eyeball 1. So this is 1 and negative 27, and it's definitely going to go through 0 and 0 and 4 and 0. Okay. Now it's going to definitely pass through 1. So just smoothly draw a curve. So you can already see it's not a smooth one. When I'm using the software, it shows perfectly, but when you're going to do by hand, just a little down. It's going to go through this point. This is a point of inflection, remember? That's 2 and negative 16. This is the point of inflection. You see this one is concave up. Then just give a little bend to show that there's a concave down. And then just a little bend at after 4, 0 to show it is concave up. Okay? So that's how we do it. Okay, so that was a nice little polynomial to be graphed. Just remember the things you have to keep in mind: the x and the y intercepts, the intervals of increase and decrease, and then a point of inflection, and also where the intervals of concavity is up and down. So all those things have to keep in mind when you do this. Okay. Let's look at a different kind of a scenario. We are having a rational function. A function given by 2 times x squared minus 9 over x squared minus 4. So the moment we look at this function, we know what this. There is a vertical asymptote because of problems when you put x to be 2 or minus 2. So that gives me domain to be all real numbers except 2 and minus 2. Okay, to find the x-intercept, what does that mean? Put y to be 0. So 0 equals 2 times x squared minus 9 over x squared minus 4. So clearly for this 0, we only look at the numerator part, and that means 0 equals x squared minus 9. So what are the two values which will make this right hand side equal 0? Negative 3, positive 3. So our x-intercepts are minus 3 and 0, 3 and 0. Okay, so what about the y-intercept? Y-intercept means put x to be 0. What do we get? Y equals 2 times 0 minus 9 over 0 minus 4. So which basically is 9 halves, because you cancel this out. Negative with the negative cancels out. You're left with 9 halves. So y-intercept, x-intercept, everything but plus minus 2. And that is a giveaway for our vertical asymptotes. Okay, so if I'm drawing the graph in my mind, I can easily see that, when I draw the graph like this, I will have plus minus 2. So simply draw a dotted line. That's one thing. So minus 2, 2. And then it's going to go through minus 3. So it's going to be a point here. That's minus 3. And a point here. It's going to cross the graph here. And it is going to be 0 and 9 halves. Sorry, here. 9 halves, which is 4.5. Okay. So notice, because when you have vertical asymptote, that means you'll have a graph here. You will have a graph here. You will have a graph here. Okay. Now we have to also talk about, is there going to be a horizontal asymptote? That's another question. Okay. So let's look at the next part. So we already got the vertical asymptotes as x2 minus 2. Horizontal asymptote at y equals 2. How? Remember, you take the limit and you take 2 times x squared minus 9, x squared minus 4 as x approaches plus minus infinity. I just took a positive infinity. And when you just take the 2 out, these are limit values we learned in our limit chapter. And now you have to look at both of the numerators. So what you have is limit. So this is what? Limit 2, x tends to infinity, x squared minus 9, x squared minus 4. Okay. Notice that here, what we are having is, to find the horizontal asymptotes, the numerator and the denominator both have the same, degree. So if you remember that in the theorem, then it means basically the limit would be the coefficients of both of them, which is 1. So it is 2 times 1. You can do that. Or you can also try, using the steps. And the steps is you look at the highest, what is the degree here in the denominator. So you divide the numerator and denominator by that x to the power 2. That's what we do. We get 1 minus 9 over x squared and 1 minus 4 over x squared. And then when you take the limit, because this goes to 0, this goes to 0, so 2 times 1 over 1, so basically it's a 2. So when I'm looking at my graph over here, what I see? I have, notice this. So I have a vertical asymptote at minus 2 and 2, and a horizontal asymptote at y equals 2. Okay, then also remember those points. So the points, it is passing through the points. So now what does this tell us? Now that's the big picture is, it says either the graph can be here or here. So that means if you are on the left hand side of minus 2, there are two paths. So graph can be up or below. Similarly, from minus 2 and 2, either the graph can be above the y equal to 2 or below y equals 2. And the graph of 2 onwards is either going to be above y equals 2 or less than y equals 2. So you can start getting the picture is when you look at where the x-intercepts are and the y-intercepts. Now remember, what is the x-intercept? The x-intercept is at minus 3. So that means the graph is below y equals 2 when you are on the left hand side of the line vertical asymptote which is passing through x equals minus 2. Okay, that's how you can start picturing the graph without even doing, you can have a rough idea, let's say, sorry, you can have a rough idea of where the graph, what would the graph would be. Now we also know it passes through the point 0 and 9/2. 9/2 is what? 4.5. So that means the graph is above the y-axis, y equals 2, because the graph is going to pass through 0 and 9, 2. So that means there is no graph beneath y equals 2 between minus 2 and 2. So, as you're doing it, you can see the picture here. Now, when it comes to greater than 2, now we also know it passes through the point 3 and 0. That's the x-intercept. So that means the graph is below y equals 2 to the right of 2. X equals 2. Remember, this is x equals 2. So whatever we have done, so we have an idea where the graph, so I will have something here, something here. Let me draw with the green, to say that, so this is where my graphs would be lying. So here I would have a graph, here I would have a graph, and here I would have a graph. Now what kind of graph it is going to be? It is going to be helpful when we do our first derivative and the second derivative, find the critical numbers, intervals of increase and decrease, and concavity. All that will show us how the graph will look in this little green squiggles I have. Okay, so let's continue. Now, to take the first derivative, you get 20x over x squared minus 4. Now, to find the critical numbers, you put the first derivative to 0. Basically, x is 0. Now, remember, I have my critical numbers here. Okay, I have what? Minus 2, 2. Now, these are my critical numbers. Oh, sorry, these are not critical numbers. These are discontinuities. Sorry. Let's do it again. You have 0 is the critical number. And we have 2 discontinuous points because that's where the function is not defined. So that's minus 2 and 2. And if I recollect, I think I was using some triangles for the discontinuity. Okay. Give me a second. I think I will just look at it. Okay. Yeah. Yes, I'm right. Remember it that when we was a discontinuity point, we kind of created a little triangle as a symbol. That this one is discontinuity. Okay, now we're going to take our test intervals. Intervals are now minus infinity to minus 2, minus 2 to 0, 0 to 2, and 2 to infinity. You all see that here. What we're going to do is now pick up numbers. Okay, for test values, pick up a number -3, -1, 1, and 3. So we're going to look at the values of evaluate the values of the first derivative at -3, -1, 1, and 3. So when we evaluate the value of the first derivative at -3, we get a negative number. That means function is decreasing. When we evaluate the values, the first derivative at -1, again it is decreasing from -2 to 0. And when you're looking from 0 to 2, that means here, remember, it's decreasing. And after the, that discontinuous point, again, it is decreasing. But then it is increasing after both of them. From 0 to 2, it's increasing. From 0 to 2, it is increasing. So what does that tell us? Now, remember, discontinuous points, and these basically are vertical asymptotes for us. So, and they're decreasing. Okay, the only thing I know, just looking at this one by the first derivative test, that means my function, just looking at this function, has a relative minima at x equals 0. And if you remember that x equal to 0 is what? There it is. That means your graph looks like this. So we already have an idea how the graph is from -2 to 2 just from that. Now to find the values where the graph is, what kind of graph is like here, on this part. So I say this is the first part. Second part, we already got the answer when we, make our little vertical asymptotes. So I'd like to know what happens in the first part and what happens in the third part. So we're going to do the second derivative test. Okay, let's do the second derivative test. Now, when you take the second derivative, you get negative 20 times 3x squared plus 4, x squared minus 4 the cube. To find the second derivative, you either have to look where the second derivative does not exist or the second derivative is 0. So when you put second derivative to be 0, we get 3x squared plus 4. No ways. So the other point is where the second derivative does not exist. It is at plus minus 2. So what we do is we have our little number line, minus 2 and 2. Now these are our second derivatives because I want to know where's the concavity up or concavity down. So we pick up some test values. So let's pick up negative 3, negative 2 to 2 is 0, and 3. Then we look at the second derivative value at negative 3, we get a negative number. So that means concave down. That means it's concave down here. That's for concavity, guys. F double prime of 0, it's concave up. And, I forgot, this is F double prime of 3, it's concave down. So what are our intervals? So the intervals from concave down is minus infinity to minus 2 and 2 to infinity. And the concavity up is from negative 2 to 2. So when we come back here, that means the graph is concave down and it's going to go through negative 3. So I can eyeball it like this. And again, it's concave down. Just, make a rough sketch, just a rough, curve over here. And also, I forgot to write down what are the open intervals where the function is increasing or decreasing. So let's write them down too. Function is decreasing from, that because very important, is minus infinity to minus 2, even though it's increasing from minus 2 to 0. But remember, minus 2 is a barrier. So you have to write minus 2 to 0. Very important. The graph is not crossing minus 2, okay, where it is increasing. It's increasing from 0 to 2 and then 2 to infinity. Remember the barriers, guys, very, very important. This little one means this is our discontinuity, and which is also saying these are vertical asymptotes. So we look at this one. That's the graph of our function. Okay, so let's look at what we actually, this is how the graph looks like. A relative minima at 0 and 9 by 2. A horizontal asymptote at y equals 2. A vertical asymptote is x equal to minus 2 and x equals 2. And this is concave down, concave up between minus 2 and 2. Okay. Now, we're going to introduce a new thing in asymptotes, that is the slant asymptote. Okay, what is a slant asymptote? Because we have talked about vertical asymptotes and horizontal asymptotes, and we've learned how to do those, find those values. A slant asymptote, it is a graph of a rational function, so very, very specific kind, where they have no common factors in this rational function and whose denominator is of degree 1 or greater. Okay, so that means you have a rational function where there's no common factors between the numerator and denominator and whose denominator is of degree 1 or greater than your numerator. It will have a slant asymptote, and when the degree of the numerator exceeds the degree, so here having no common function, and when the degree of the numerator exceeds the degree of the denominator by exactly 1. So in other words, if you have a function, say x plus 1, okay, I say x squared plus 1. The denominator has to be degree 1 or greater. In other words, I cannot have a constant here. So if it is x squared plus 1, this is degree of the numerator exactly greater. So I would say x minus 2. So this is going to give me a slant asymptote, because the degree of the numerator is first of all greater than degree of the denominator, but by exactly one value, and you are having rational functions. In other words, a polynomial over a polynomial. Remember when we talked about horizontal asymptotes? What were the horizontal? Just a quick recap of the horizontal asymptotes. In horizontal asymptotes, if the degree of the numerator is less than the degree of the denominator, okay, what was the horizontal asymptote? Y equals 0. Classic example, fx equals degree of numerator is less than the degree of the denominator. Okay, that was one scenario. Okay. Second, when the degree of the numerator is the same as the degree of the denominator, then y was the leading coefficients. For example, let's take an example. Fx here is 3x cubed plus x over, say, 9x cubed minus 1. In this one, both of them have the same degree, so 3 over 9, y equals 1/3, which is basically 3 over 9. Okay? Now, what happens when the degree of the numerator is greater than the degree of the denominator? When the degree of the numerator is greater than the degree of the denominator, we said the limit does not exist. Okay, we agree. But here, a slant asymptote is one specific one. It says, yes, the degree of the numerator is greater than the degree of the denominator, but it exceeds exactly by 1 degree. That's the most important part. And the degree of the denominator has to be 1 or greater. You cannot have a constant, in other words. Okay? Because degree 1 means x has to be present, a variable has to be present. So that's a classic example of this will give us a slant asymptote. Or we can also have fx, say, x4 minus, say, x3, and denominator is, say, x3 plus 2. Once again, we will have a slant asymptote here, because degree of numerator is greater than degree of denominator, but the degree of the numerator is exactly 1 more than the degree of the denominator, and all these factors are taken into consideration. Okay, so the next example, guys, is going to involve a slant asymptote. And when you have a slant asymptote, you cannot have a horizontal asymptote. Remember that, because horizontal asymptotes happens in these two scenarios. When the moment degree is greater than numerator greater than degree of denominator with this specific condition, we are having a slant asymptote. Okay, let's go ahead and do that. So we have a function x squared minus 2x plus 4 over x minus 2. First thing, the moment you notice everything is well, but 2 is not happy when you plug in when you plug in 2x for 2, you have a 0 in the denominator. So that means domain says everything but not 2. And we also know that is where the vertical asymptotes are. X intercepts, y has to be 0. Let's put that. So 0 equals x squared minus 2x plus 4 over x minus 2. That means x squared minus 2x plus 4 to be 0. Right? Okay, so can we factor this one out easily? Let's see. Now, what are we going to do? Do you guys remember because it's not easy to factor, remember? X minus 2 here. So we are going to see, can I write x minus 2 the whole square? No, it's not going to work, right? So what are we going to do? We are going to say, let's apply our, the quadratic formula to see it. Because I can't easily factor something. 4 is 2 and 2, no, it's going to work. Okay, So let's do that. X equals, now if you remember, it is, if your function is ax squared plus bx plus c, if you want to find the quadratic formula, that is minus b plus minus square root b squared minus 4ac over 2a. Okay, so my b is negative 2, so this would be 2 plus minus square root minus 2 squared, which is 4, minus 4 times a is 1 and c is 4 divided by 2. What are we getting? 2 plus minus square root 4 minus 16. You're getting complex numbers. We are dealing with here only in real numbers. Not possible. So what you're going to get is we're going to get complex solutions, remember, from here. But in our analyzing, we are only assuming real numbers. We're not looking at complex solutions, okay? That's why there are no X intercepts here. So you have to keep in mind, where are my values? Because we're talking of domain of real numbers. So if you notice, it is real numbers. This is giving me a complex solution. That means we're not taking any complex numbers here, okay? Now, when it comes to, that's why none is the x-intercept, y-intercept. That means put x to be 0. What do we get? Y equals 0 minus 0 plus 4 over 0 minus 2 minus 2. So 0 and minus 2, y-intercept. Okay. Now, let's look at the vertical asymptotes. But remember, what was our function? Our function was x squared minus 2x plus 4 over x minus 2. So 2 was not in the domain, it is a vertical asymptote, okay? Horizontal asymptotes, now notice, the degree of the numerator is first of all bigger than the degree of the denominator. So no horizontal asymptotes. Is there a possibility of a slant? Yes. Why? Because the degree of the numerator is exactly more than the degree of denominator by 1. So yes, so there is a slant asymptote. Now what do? Now to get the slant asymptote, we will do the long division. So long division, I hope you guys remember, is this. X squared minus 2x plus 4 divided by x minus 2. So we have to get rid of x squared. So what do? We multiply by x. X times x is x squared minus 2x. Now do the normal division you do. Change the signs. What do we get? A 4. So now the degree, the denominator, sorry, the remainder is less than the divisor here, which is x minus 2. So what we do is you write, this formula is now written as x, the quotient, plus what is the remainder divided by the divisor here, which is x minus 2. So when you take the limit, what happens here, guys? Now this limit is limit x tends to infinity of x plus the limit 4 over x minus 2 as x tends to infinity. This we already know is going to be 0, because if we divide by x, remember this is your horizontal asymptotes. Do you see that here? So this is going to be 0 because it's 4 over x. Okay, let me just do the math once again. For this one, limit x tends to infinity 4. Remember the highest degree value, the degree of the denominator is 1. So you divide by x to the power 1 and x minus 2 to the power x. So you are having limit x tends to infinity 4 over x, and this is 1 minus 2 over x. So what does happen? This goes to 0 as you take the limit, and this goes to 0. You get 0 over 1, 0. So when you apply this limit, this is 0. But notice, as y, the slant asymptote is, as x increases, y is equal to x. So that's how you write this one, a slant asymptote. If you can write if you see that there is going to be a numerator which is exactly 1 degree more than the denominator, you apply the long division and one of the expressions will definitely go to 0. The other one which is left is basically the slant asymptote. So this one is y equals x. No matter whatever the x value, this will be that. So that is my asymptote. Okay, so let's draw, we have done a lot of things. So let's draw a little graph over here to get an idea what's going on. We know at x equal to 2, it is a vertical asymptote. Also, we have a slant asymptote at y equals x, which is given like this. Y equals x is a line passing through the origin at a 45-degree angle. And if you also remember that there is only y-intercept 0 and -2 and nothing else, no x-intercepts. So that means the graph is never crossing this part. Now 0 and -2, that means there is where one of the values would be. Okay, so in other words, either the graph is here or the graph is here. So the graph is here. Let me just draw little greens where the graph can be. Either the graph can be here or the graph can be, let me just, just draw little circles. Or the graph can be here with a little squiggle and this, or this whole part is the graph, or this part is the graph, or this part is the graph, or this part is the graph. So there are 4 places the graph can be. Now, between 0 and 2, so that means in this part, so the first part, the second part, and the third part. Now, when you look at these 3 parts, because the graph is crossing through the point 0 and -2, which we already know. So this is where the graph would be. Okay, in the second part, the graph is below. Now we have to figure out where it is over here, how the graph behaves here. Remember, it's not going to cross the x-axis. You've got to be very careful. It's not going to cross the x-axis. Okay, neither the graph is going to be, so that means the graph, it cannot go like this. Do you all see that over here? This part, the first part, we won't have the graph. The reason is because if it is here, it will cross somehow the x-axis. And this tells me either the graph is up or down. So in this one, we are only going to have the graph in this part. Here is the graph going to be, because this is a line which is not going to let it go. Okay, this is a slant asymptote. So the graph is going to be here. So now here, either the graph is here or here. So in the second and the third part, what we notice is, so the first part as is talked about. So you have to think about a lot of things here. So then it is either going to be, so this part, the second part, or this part does. Okay, so it is going to be here. Remember, as the graph goes negative, the values are going to be coming out over here. And now in the third part, either it's going to be a little squiggle with a little red dot in the middle and a squiggle with a circle and a red dot. So either of these two, there will be a graph, and which will help us when we do our little more, critical numbers and we do our second derivative. So I've just given you a brief idea how the graph will look like. Now let's look at the critical numbers, guys. So in our critical numbers, what is f prime of x? The critical number is x, x minus 4, x minus 2 the whole square. There are 2 critical numbers, 0 and 4. So once again, now 0. Now remember, there is one discontinuous point, and that is at 2. So this is my critical number. 2 is my discontinuity, my little triangle, and 4 is my critical number. So I will have 4 intervals, minus infinity to 0. One interval is here. Interval from 0 to 2. Interval from 2 to 4. And 4 to infinity. Pick up test values. Minus 1, 1, 3, 5. Now evaluate the first derivative at minus 1, 1, 3, 5. Now when we evaluate at minus 1, it is a positive number, function increasing. When it is at 1, that is between 0 and 2, it is decreasing. When it is between 2 and 4, it is negative 3. Again, it is decreasing. And when it is 5, that is in the interval 4 to infinity, it is increasing. So what are the intervals of increase? The intervals of increase are minus infinity to 0 and 4 to infinity. Intervals of decrease are 0 to 2 and 2 to 4. Remember, you cannot join them because 2 is a point of discontinuity. This, remember, is your vertical asymptote here. Okay, now when I look at this one, it tells me two things. Now, I can apply the first derivative test, and what I see, when I go according to the graph, this means there is a relative maxima at 0. When I go at 4, the critical number, it goes down and up. That means this is a point of relative minima. So we already got relative maxima minima by just doing the critical numbers in open intervals for increase and decrease. Okay, so if I try to add more to the graph, I already know. So let's do that also. So remember the graph. 2 is my point where it is the vertical asymptote. The slant asymptote is y equals x. So this is y equals x. And this is x equals 2, the vertical asymptote. Okay. Now remember, I'm going to repeat it again. So the graph can be either in this part, this whole part, or in this part. Okay. Now we also know it is passing, so the graph can be, remember that this part, like let me just use say blue here. So the graph can be here, or it can be in this little circles. Okay. So that's two places where the graph can be, but we also know that the y-intercept is the point, this one, which is 0 and negative 2, if you remember. So that means the graph cannot be on this part, it is only going to be in the little circle spot. So let's remove this part here. So the graph cannot be here. Okay. Okay, let me clean it up and just draw the lines. So the graph is where these little circles are, and it's passing through this point. And also we know from here it is a relative maxima. So that means the graph will go like this. And it has to remain between these lines. Okay, so that's one thing. Now, the other thing is the graph has a relative, according to this, has a relative minima. Okay, and it is at 4. Now, what is the value of the function at 4? So that means it has, we said, a relative minima at 4. And so what is that point? F of 4. Now, what is f of 4? Our function was x squared minus 2x, remember? So it is this function. If you remember, the function was, we could write like this also, x squared minus 2x plus 4 over x minus 2. Or we can write like this as x plus 4 over x minus 2. So when I plug in the value 4 plus 4 divided by 2, so it is basically 6. So that means this point, now this, remember this point is 2. So 4 and 6, so that means this gives me an idea that my graph is somewhere here. Okay, let me put this y equal to 6 here. So, I'm just showing you there are so many ways you can get the graph by just learning what you're doing and applying it. So at 4 and 6 somewhere here. So that means my graph will be somewhere here. It is a minima. So I already have my graph. Just what we're going to do is we're going to do the second derivative and confirm where the graph is concave down and concave up. Okay, so you will see the graph is concave down from 0 to 2, concave up from 2 and above. Okay, let's go ahead and do it, guys. So we find the second derivative, and the second derivative is 8 over x minus 2 cube. That means second derivative is 0. That is, 8 cannot be 0, right? So that means to find the concavity, we'd need to know where the second derivative does not exist. It is at 2. So that's what we will be using to find intervals. So that interval is 2 minus infinity to 2. So pick up a test point value, and I pick up a test value after that. So it's 3 and 2. Second derivative at 0 is minus 1. Okay, and second derivative, that means concave down. And second derivative at 3, okay, another typo, is 8 concave up. Now remember the graph which we just had shown you. We had a graph like that. That's y equals x, the slant asymptote. It's passing through the point 0 and minus 2, and we said it goes like this, which is a point of maxima. And then we have a vertical asymptote, which is given by x equals 2, and then 4. It was 6. Do you remember that? And then we said it is the minimum. So minimum means this is the smallest value, and the graph would go like this. Just from our first derivative test and all the things we learned. And now this confirms. From minus infinity to 2, remember this is the point 2. Concave down, we have the graph. From 2 to above, the concave up. And that's exactly what these signs are saying. And there is no point of inflection. Remember this guy's 2, it is though concave down to concave up, but 2 is a point where it is a vertical asymptote. That's why there is no points of inflection. And to write the concave down, it is minus infinity to 2, concave up, 2 to infinity. Okay, so that's what we have just worked out. And this is when you put it on a little software or a graphing calculators or Desmos.com graphing calculator, which I've shown you many times. This is what your graph looks like. So this is the point of relative minima, 0, minus 2. And this point, 4 and 6 relative. Oh, sorry, this is relative maxima, 4 and 6 is relative minima. Well, I hope you guys are able now, you have understood a little bit of how things we have done. Whatever we guys have done, I basically put it together in section 3.6. Okay, and now I would like you to practice. I've given you 4 problems, and I want you to do all the guidelines. In other words, I want you to find the domain, x and y intercepts, the asymptotes, the critical numbers, the first derivative, open intervals, increase, decrease, second derivative, find the open intervals for concave up and down, points of inflection, and relative extrema. I've given all possible kind of scenarios, a cubic function, a polynomial of degree 4, a rational function, and the last function has a slant asymptote. So please practice them. Thank you.